All right, so we're going to continue section 11.3, the dot product. So we ended our last video with just doing an example. So now let's introduce some tools that we can, or some ways that we can use the dot product to determine things about vectors. So first, the dot product tells us if two vectors point in the same general direction. So if A dot B equals 0, then theta is equal to pi over 2. And when I'm saying theta, I'm talking about the angle between the vectors A and B, and I'll specify that at the end of this. If A dot B is less than 0, then theta is greater than pi over 2. So if the dot product is less than 0, then the angle between the two vectors is greater than 90 degrees. So we say they kind of don't point in the same general direction if the dot product is negative. And then if A dot B is greater than 0, then the angle between the two vectors is less than 90 degrees. So we would say that they kind of point in the same general direction. So where theta is the angle between A and B. All right, so now another key characteristic that we'll use. So two vectors A and B are perpendicular. And we've already kind of addressed this in the last statement. If and only if the dot product is equal to 0. All right, so if we had up above, if the dot product is equal to 0, then the angle between the two vectors is 90 degrees, so they're perpendicular. But if they are perpendicular as well, so if you know that the angle between them is 90 degrees, then you also know that their dot product is 0 immediately. All right, so let's look at an example from our textbook. So we're on page 728, number 8. Which says in exercises 8 and 9, determine whether the vectors PQ and PR are perpendicular. So they give us some points. They don't even give us the actual vectors, so we have to find the vectors ourselves. So the point P is 2, 1. The point Q is 1, 4. And the point R is negative 3, 2. And they said determine whether the vectors, so we're going to determine if the vectors PQ and PR are perpendicular. So first we have to find these vectors because we don't have those vectors. We're just given the points. So we'll go back to an earlier lesson where we looked at how do we find a vector given points. So PQ is equal to. So remember here, it's a little bit counterintuitive. We're going to do 1 minus 2 and then 4 minus 1. You don't want to do 2 minus 1 because if you do that, you'll be finding the wrong vector. So to find PQ, we're going to do 1 minus 2 is going to be our first component. And then 4 minus 1 is going to be our second component. So these vectors are in 2 dimensions versus being in 3 dimensions because our points are all in the plane. They don't have a z coordinate on there. They only have an x and a y coordinate. So here we get the vector -1, 3. And then we need to find the vector PR. So now to find PR, we're going to do -3 minus 2, comma 2 minus 1. So that gives us -5, 1. So now we have our 2 vectors, and now what we can use is we can use the 2 vectors are perpendicular if and only if their dot product is 0. So what we can do is now take the dot product of these 2 vectors and see do we get 0 to determine whether they're perpendicular or not. So PQ dot PR, and the order in which you take the dot product does not matter. Now that's not the case with a lot of things, but here the order of the dot product doesn't matter. So here we're going to do -1 times -5 and then plus 3 times 1, which gives us 5 plus 3, which gives us 8, which is not 0. So those are not perpendicular. So not perpendicular. All right, so now the next thing that we're going to talk about is what's called the projection. So let A be a non-zero vector. The projection of a vector B onto the vector A is, so first I'll show you how to compute it, and then I'll sketch a picture of what actually is going on in this projection. So the notation is PR for projection, but the projection itself is a vector. So you're going to put a vector hat over that PR, and then there's a subscript A, and A is a vector, so it has a vector hat. And then there is a B, and it has a vector hat because it's a vector. So the projection of B onto A, and so like we have the A down here is the subscript because it's the one that's being projected onto. Now, what is happening? How do you compute that? The way you compute that is you do A dot B, and you divide that by whatever vector you have down here. You take its magnitude and you square it. So the magnitude of A squared. So you compute all that. This is just going to be a number because the dot product's a number. The magnitude's a number. You square it, it's a number. You do the that quotient's a number. So we just have some scalar right here. We take that scalar and we multiply it by the vector A, the vector that we're projecting onto. So we get a vector in the end, which is why we have a vector hat over the PR part. And it is all that vector is just our vector A times some number. and this number is dependent upon what our vector B was in the first place. So let's sketch what do we have here when we do this scalar projection. I'll sketch it on the next page because I don't want it to be too small. So say we have our vector A, and you can sketch the vectors however you want to. So this is our vector A, and we said it is not the zero vector. Actually, let me use it. Let's make that I'm going to make that my vector B, just because I want to use a different color for A. So that's our B. And we said that A is not the zero vector. So what I'm going to do is I'm going to make that my vector A. So there's A. Now the way we do the projection of B onto A, and we're not actually in computing this, you're not going to have to sketch the picture, but just so you can see what's actually going on. So we're given some non-zero vector A, and we take some vector B. And remember, if these vectors, their initial points didn't meet, we can move them so that their initial points do meet. So we can always do this formulation as long as A is some non-zero vector. So then what we do is we drop what we would call a perpendicular from B onto A. So this right here is a 90-degree angle there. And the projection of B onto A is just this vector right here. So it goes from there out to here. And that's the vector, the projection of B onto A. So this would be this vector right here. All right, and it works regardless of where those vectors are in relation to one another. So that's the most simplistic scenario, but let me draw another scenario underneath it that is just as feasible. So say for instance, this time doesn't matter. So say for instance, our vector A was that vector. So that's our vector A. And our vector B was this vector. Now to do the projection onto A, what you have to do, we're not going to drop a perpendicular. We can't drop a perpendicular in this direction because it's not perpendicular. We still have to drop it perpendicular to the vector A. So we will drop this down like that. And then our projection vector will be that vector right there. So this now will be the projection of B onto A, where that's a 90-degree angle right there. All right, so now what we'll do is we'll do an example computing the projection vector. So let's look at number 14 on page 728. So number 14 says in exercises 13 through 14, find the projection of the vector PR onto the vector PQ. Okay, so here we're not given the vectors, we're just given the points, so we have to find the vectors ourselves. So P is 1, 2, 3. Q is -1, 0, 1. And R is 1, 1, 0. So, and we are interested in PR and PQ. We have to make sure we do find the correct vectors and then do the correct projection as well. We want to project PR onto PQ. So let's find PQ. So PQ is going to be -1, -1 is -2, then 0 minus 2 is -2, and then 1 minus 3 is -2. And then PR is the other vector that we want. So PR is 1 minus 1, which is 0, 1 minus 2, which is -1, and then 0 minus 3, which is -3. And we are projecting PR onto PQ. So this is what we want. So now to do that, let's get all the aspects from our formula that we need. We need to do the dot product of these two, and then we need to divide by the magnitude of this one that's down here. So the way I kind of remember is whatever is whatever's at the bottom in the notation is in the denominator over here, and it's also going to be the vector that you multiply at the end. So the dot product is what's in the numerator. So this is PQ dotted with PR. You're going to get -2 times 0, which gives you 0, plus, and I'll write it out up here. So -2 times 0 plus -2 times -1 plus -2 times -3. I was going to write out the formula again in terms of this, but it was going to take up a little bit too much space and I was going to run out of room. So if you want to, you can rewrite the formula in terms of PQ, the vector PQ and PR. So your numerator would be the vector PQ dotted with the vector PR, then divided by the magnitude of PQ squared, and then put all of that in parentheses on the outside. You will put the vector PQ again. So then this is all over the magnitude of PQ and then square that. So the magnitude of PQ would be underneath the square root. And I'll write it even though we're going to get rid of the square root because we're going to take it and then we're going to square it. So that will be -2 squared plus -2 squared plus -2 squared. That's where we compute that magnitude. Put all this in parentheses, and then on the outside, we just put the vector PQ. So the vector PQ is just -2, -2, -2. So -2, -2, -2. Oops, sorry, can't see that last -2. So that will be, and then we simplify this. So we get equals 0 to, okay. So we would get 0 and then plus the 2 and then plus the 6. So we get 8 over the square root 12, or sorry, the square root of 12 squared. So that's just going to be 12 and then times our vector -2, -2, -2. So you could leave this and that, I mean, you would simplify that, or you could multiply this through. The reason that it's okay to leave it is because sometimes we like to see the projection as a scalar multiple of our original vector. So that's sometimes why we'll leave this in this form without distributing that through there. So you could distribute that through, or you can leave it out. Either one is fine. All right, so we'll stop this portion of 10.3 there, and then I'll continue or finish off this section in our next video.